Hello dear colleagues and welcome to Civil Curious channel. In this video we are going to talk about welds, type of welding and type of welds, weld equipment and etc. Especially weld calculation. Let's get started. Uh, as you know, we have some types of welding in civil engineering, and the most popular of them is fillet weld. Let me write our topic. I'm gonna write types of weld. First of all, I'm gonna write the most popular, which is fillet weld. You know, the second one is groove weld. And the third one I'm going to talk about is uh, a slot weld. You know, actually, groove weld and penetration weld actually are the same. Penetration weld. We use these weld in seismic works and area or zones that seismic issues are important for us. For example, the area that column beams arrives to be columns. This area should be seismic, should have seismic build. Okay, let's continue. Uh, First of all, I'm going to show you the fillet weld. For example, we have a steel plate like this, which is going to be welded to this plate. The type of welding that is filled here in this area is called fillet weld. We use fillet weld in this area. Okay, and let me show you more accurate. This is our weld. But this dashed line I've just draw is the simplified or engineered shape of fillet weld, but the real shape has curved shape. This is actually gonna be the shape of fillet weld in real. We have this dimension of weld as weld dimension, which we call it weld dimension, which we call it A, and we have here the weld dimension actually A2. Both of weld dimension in this in our tutorial are the same and are A. And we name this area, this length of weld, we name it effective thickness of weld, which we show that with TE. We call it effective effective thickness of valve. Okay, but let me tell you the relation of the calculation of effective thickness that we call it TE. TE in fillet weld, when the dimension of weld be the same in both direction, will be equal to radical 2 divided by 2 times the times A, or the weld dimension, okay, which is approximately equal to 0.707, okay, of A, you know. But we have another case that dimension of fillet weld are not the same, like this circumstance, okay. For example, in this direction we have A1, and in this direction we have A2, you know, and the effective thickness TE is equal to, in this circumstance, we have TE, which is equal to A1 times A2 divided by radical a square meter of A2 plus square meter of A1, you know. This is the calculation of effective thickness of, for example, fillet weld. But if you all agree, let me uh, solve a problem for you uh, in fillet weld to uh, okay. For example, we have a weld, fillet weld, which have this shape. The the dimension of weld in this direction is 5 millimeter, and in this direction, for example, is 4 millimeter, you know. And we're gonna calculate the effective length of our fillet weld, which is equal to, our TE is equal to 4 times 5, you know, divided by radical square meter of 4 plus square meter of 5, which is equal to 20 divided by radical 45, you know. Let me calculate that. Our answer is 20 divided by radical 45. Our answer is 2.98, which is approximately 3 meter. Our effective thickness of weld. This is fillet weld, and if you all agree, I want to show a clip of fillet weld for you. You know, let's watch that. Look at this video. This is kind of fillet weld, a weld of brace to a gasket plate. You can see, and now you are watching the fillet weld completed, which is completed, and this man is cleaning the weld, you know. Okay, this video, this man is operating another fillet weld. This weld is down to up, is a bit hard welding work, you know. And this thing that you are watching is electrode, is one of equipment of welding, you know. Okay. Now we get familiar with the fillet weld, you know, and we have learned the effective thickness of fillet weld. Okay. Now I want to tell you what is penetration weld. You know, suppose that we have a plate here, and we want to connect that to another plate. For operating fillet weld, this area, this section of plate should be connected, you know, and be connected to another part. Let me draw that again. Okay, and another part in the another part, another plate should be connected to. This is the section of another part, you know. And this area should be filled with weld and will be so strength so that we can use them in earth in seismic works in the our building, you know. Let me tell you that penetration weld is used in beam to column joint and other thing in building, you know, because we have for example special moment frame, intermediate moment frame, and in these frames seismic well is really important, and we are and we have the use of penetration well in these works. Okay, that were the penetration valve. Okay, in the penetration valve we have a complete penetration valve and one incomplete, you know. And for example, this penetration valve is complete because all the area is filled with valve. But suppose that this area has not enough valve, for example, this area, and that was not complete, it was incomplete, you know. We have two type of penetration valve, completed and incompleted. Okay, uh, let me find another thing to tell you about valves, which is important for you. Okay, Uh, that was enough now, everybody, uh, uh, for introducing type of weld. I'm going to tell you, I'm going to enter to calculation of welds. Okay, uh, in the calculation of weld, uh, we have some types of building that I'm going to tell you the most important of them. You know, for example, we have one strip of weld like this. You know, which has dimension d. You know, and the moment of inertia of this weld, which we call it IP or J in civil engineering, is equal to d cubic meter of d, or d to the power of 3 divided by 12. This is the calculation, you know, times Te, the effective length, the effective thickness of weld, you know. And in calculation, generally, we suppose Te to be 1, you know. This is actually most common shape of weld. And in some calculation, in some cases, we have welding like this. We have two strips of welds which have the dimension of D, and the distance between welds are B, you know, and the J, or moment of inertia of weld, is equal to D times 3 times B to the power of 2 plus D to the power of 2 divided by 6, you know, times Te, which our Te is equal to 1. You have to uh, memorize this equation, you know, because when you want to solve a problem of weld, you can easily solve it. Okay, and we have another shape of weld which has channel shape. Okay, the distance is D, and here we have, for example, this is the center of our weld, which is shown by X bar, you know, and the distance between center of weld to the end of the weld, we call it B. You have to actually memorize that, and it has actually long equation. I'm going to write for you. J is equal to IP, which is equal to 8 times B to the power of 3 plus 6 times b times d to the power of 2 plus d to the power of 3 divided by 12 minus b to the power of 4 divided by 2 times b plus d, and all of them times the effective thickness, which our effective thickness is 1. Okay, these were the calculation of moment of inertia of our most common strips of weld, cases of weld in civil engineering. Okay, we have a, uh design strength for weld, which is shown by thing that I'm gonna write for you. For example, when we made a weld in every part of our building, it has a nominal strength, and in the earthquake or other loading, uh, it will be under another load that we call it action. In civil engineering, the action affected on will should be less than the nominal strength of will, which is called, we call it phi times Rn, you know, and we have Rn, uh, like I'm gonna write for you. We have Rn, which is equal to Rn is equal to beta times F and W times AWE, and I'm gonna illustrate that for you. Uh, Beta is a coefficient which has a specific value, and the F and W is the nominal tension, is the nominal tension of weld material, or an AWE is the effective area of weld, is the effective area of weld, in the fillet weld. In the fillet weld, we have phi, let me tell you, in the fillet weld, we have sorry, we have phi, which is equal to 0.75, and the and we have F and W, which is equal to 0.6 times FUE, which is equal to ultimate strength of our electrode, you know, of weld material, you know. And if and let me illustrate beta for you. Beta is 1 or 0.85 or 0.75. If we have our uh, testing in the site, we have beta as a 0.75. If we have our test, in the factory, we have beta as 0.85, you know. Okay. And for electrode, we have sub type of electrode. For example, we have electrode E60, and we in for electrode E60 we have FUE, or ultimate strength of electrode is 420 megapascal. Okay, and for electrode E70 we have FUE to be 490 megapascal. You know, uh, these were the actually brief calculation of well that I have told you. These were actually was very important. Now I want to solve a problem for you and tell you what is happening when a weld is subjected to uh, shear force, or torsion moment. What is happening when we have these cases. You know, I have already prepared this picture for you. As you can see, we have connected to two plates to each other, which were connected with fillet weld. Okay, and this weld is subjected to a load which is not uh, in x or y direction, and it has a bit angle. Okay, this shape of loading will yield to weld will yield that the weld have both shear force and torsional moment. Okay, but we can actually divide this load to PUX and PU1, you know, and angle of alpha that you can see. And the EX and EY are the distance of load from a center of valve. Okay, let me center of area of valve. Okay, uh, let me address these loads for you. The PUX is equal to PU times cosine of these angle, cosine of alpha. Okay, and PUY is PU times sine of this angle. Okay, and we have the torsional moments which is equal to PUY, this component, times EX, minus PUX times EY. Be careful about the direction of torsional moment. Okay, then we want to solve a problem like this. At first of all, you have to be careful to calculate first. Let me write that here. Calculate that first. First of all, you have to determine the area center of weld, or G. Okay, and then you have to calculate the distance of load component from the area center of weld, which are E1 and EX. Okay, and then you have to calculate other things of like moment of inertia, or effective thickness, and effective area, and other things. Okay, but you know that I have told you in the previous papers that moment of inertia of is equal to J and is equal to Ix plus Iy, and I told you in the calculation of weld, we suppose the effective thickness of weld to be 1. Okay, and in the last part we have to use the tension affected in points, other points, different points of weld. For example, we want to calculate tension on a point of A in this, let me change the marker, in this area. For example, we want to calculate the effective tension on this point A. Let me go to another page. Okay, as I said you before, our strips of weld has this shape. Okay, has this shape. And this is the area center. This is the center of our weld. Okay, we have PUX component in this direction. We call it PUX, and we have PUY component in this direction. And we have the torsional moment in this direction. Okay, we call it TU. I can approximately make equal this this coefficient, this component, to, I'm gonna make it a bit easy. You know, separately, we can write that this is my strip. Okay, it has, it is subjected to PUY separately, you know, and in this point A, we have FUVY, the tension affected in point A, we call it V. Okay, plus I have the change the marker. Sorry. This is my ball, which now is subjected to horizontal coefficient of ball. We call it PUX, and we have here point A, which is equal to FUVX, the tension in X direction, plus I'm gonna I'm drawing the shape of loads separately to have a better comprehension of what is happening involved. Okay, I apologize for bad drawing for you, everybody. And we have here the torsional moment. We call it TU. you know and the distance from the center of weld to point A, I'm gonna write that x of A, and the distance between point A to center from y direction is YA. And the direction of torsion is clockwise. For example, we have our torsion in the clockwise, and for point A, which is here, we have tension like this. This is the direction of torsion, as is the point A, and we can write this coefficient as two coefficient. We have here the tension of torsion, and these are the component of these component. We can write that FUT by the Y component of tension torsion component, and we have here FUX of torsion component. These were the tension uh, that are created in point A. We can write all of these coefficient for another point like B, you know, and be careful that in uh, point B, the direction of torsion component is different, you know. But if you all agree, I will write I will write the direction of tension in point B for you, okay? But now I want to calculate the tension in a direction, in a point of A, okay? For example, in point A we have in point A in point A we have the tension of vertical component or FUVX, is equal to PUX divided by the effective area of weld, you know, and we have shear tension in Y direction or FUVY be equal to PUY divided by AWE, and for torsion we have FUT in X direction we have the uh, the whole torsion times the distance from point A to the center of weld, or TU times YA divided by J. I told you before what J is. And we have FUT in Y direction to be TU times XA or XA divided by J. This is the method of calculation of weld of tension which is subjected to in A point, which is created to point A, okay? And for point A, now we want to calculate the whole tension. In point A we have the total tension, which is the ultimate tension in point A. We have FUA to be radical FUVX plus FUTX, to the power of 2 plus FUVY plus FUTY, to the power of 2, okay? These were the method of calculation of uh, created tension in point A, and ultimately we calculate if u and make it less than Ru, which is created in our valve. Okay, this is the code-based calculation of tension, and all of these calculation uh, applies to another point, like B, for example, here in this point. All of the calculation applies to point B, you know. Now I'm going to solve a question for you, everybody. Suppose that we have two plate which is going to be connected. These are our shape is like the shape that I illustrate for you now. Okay, this is another plate which is going to be connected. This is the continue. Okay, and this area is going to be weld, and this is the center of weld, and the whole depth of weld is 30 centimeter. Okay, and our torsion which is affected on the weld is 1. Our TU is 1 ton meter, is 1 ton meter. Okay, and this dimension of weld is 15 centimeters, and the distance between center of weld to end of the weld is 3.75. I mean this area, this distance is 3.75 centimeters. Okay, let me solve this problem. We want to calculate the maximum. We want to calculate the FUT in X direction and FUT in Y direction. Okay, FUT and FUTX and FUTY is equal to. Okay, in the previous paper, I told you a equation for channel shaped weld. We had this shape, this equation for channel weld. We had J to be equal to 8 times b to the power of 3 plus 6 times b times d to the power of 2 plus d to the power of 2, sorry, d to the power of 3 divided by 12 minus b to the power of 4 divided by 2b times d. Okay, that was our equation. And we have here b to be 15 centimeter and our d is 30 centimeter, you know, and that's enough. And let me calculate that. J is equal to 8 times 15 to the power of 30 plus 6 times 15 times 30 to the power of 2 plus 30 to the power of 3 divided by 12 plus, sorry, minus minus b to the power of 4 divided by 2 times b plus d, and I have calculated that, and the answer is 10 406 centimeter to the power of 4. Okay, and we have here, if utx to be equal to our torsion is 1 ton meter, we can write that 1 times 10 to the power of 5, you know, times b, or 15, divided by J, which is equal to 10 406, which is approximately equal to 144 kilogram divided by centimeter to the power of 2. You know that FUTX, let me review that for you. We had FUTX to be equal to TU, which was 1 times 10 to the power of 5, TU times YA, you know, divided by J. We have here point Y, point A is here, and the maximum distance of Y to the center of weld is 15 here. This is center of weld, and we have another distance which is 15 here, 15 because this distance is 30, you know. Because of that, my YA was 15, I write it here, and my TU was 1 times 10 to the power of 5, and this is that was our J, or moment of inertia. Okay, and we have FU TY to be TU times XA divided by J. And the XA is 15. We have this distance as 15. And we want to calculate this distance. Let me write that. XA is 15 minus 3.75, which is equal to 11.25 centimeters. Okay, and we have here FUTX to be equal to 1 times 10 to the power of 5 times 15, sorry, times 11.25 divided by 10 for 106. And our FUTX is equal to 108 kilogram divided by centimeter to the power of 2. These were an example of calculating a weld under both shear force and torsion moment. Actually, it's a very, very important and practical example for civil engineers. Okay. By now, I have introduced types of weld, which were slot weld, penetration weld, fillet weld, and I have calculated the effective thickness of weld for you, and then I have introduced calculating of moment of inertia of weld, and in the end we have addressed the calculation of weld under both shear force and torsion moment. And in the end, let me address some most important thing for you. We have another case that our weld is subjected to both shear force and flexural moment. Let me draw that for you. I just want to introduce that for you, and in the next session we will completely go into that. This is, for example, our column or another vertical element in our structure, and we have here, for example, a plate or a cantilever which is attached to our column. And this area is filled with weld, and we have here a shear force, which we call it PU, and the distance between PU and the end of the plate is E, and be careful that when this plate want to be attached to this column, we have two strips of these welding. Our shape of welding is approximately like this. This strip and this strip. And these two strips is subjected to both shear force pu and moments and flexural moment, which is shown with this mu. Can you suppose this moment mu, how it's gonna work? If you look that carefully, there is not any torsion here. It's a moment frame. You have to be careful to distinguish between moment, flexural moment, and torsional moment. And here our uh, moment, flexural moment, is mu, which is equal to pu times e. you know this is the relation. I just want to introduce this circumstance for you, and I hope that you all enjoy it. And in the next session, we will go to calculation of this circumstance. I hope that you all not be tired, and I hope that you all enjoyed this video, everybody. And if you like it, I want you all to subscribe this channel to motivate me to create more videos for you. Thank you, everybody. Thank you very much.